Hello everyone. In this module, we are going to solve some of the problems based on 1H NMR spectroscopy, and also we will solve some composite problems involving UV, IR and proton NMR, followed by isomer identification using 1H NMR values. So this constitutes exercise 3. Before we take up some problems, we will quickly brush up our memory regarding what information we can obtain using UV, IR and PMR. In UV visual spectroscopy, you can identify whether conjugation is present or not and whether aromatic present is, is there or not in the organic compound. As far as IR value are concerned, you can identify the important functional groups present in the compound. Whereas when coming to 1HNMR, it will give you how many types of protons are present in the molecule as well as in which environment they are present. That means how many types of protons as well as how many types of environments are present in the molecule can be easily identified by looking at the 1HNMR values. Let us quickly recall some important IR functional groups and their stretching frequency. If it is ether, then it appears around 1075 centimeter inverse, ester 1740 centimeter inverse, carbonyl 1715 to 1730 centimeter inverse, depending on the various groups it is attached to. If it is aldehydic, it is 1670 centimeter inverse, anhydride 1670 centimeter inverse. If it is aromatic C double bond C, that means if there is any benzene ring and C double bond C present in the benzene ring will show value around 1500 to 1600. Presence of nitro will give a stretching frequency at 1530 centimeter inverse. Presence of acetylenic will have a characteristic peak at 2250 centimeter inverse. Aromatic CH stretching will have value around 3050 centimeter inverse. Alcohol will show around 3330 centimeter inverse, whereas amine will have value around 3500 centimeter inverse. Having known all this basic information, before we go into solving the problems, we shall take up the problems now. The first problem is explain why orthoproton absorbs at delta 8.80 ppm while the paraproton resonates at 8.45 ppm in phenyl dimethyl methane carbocation. So when you attempt to solve such kind of problem, first you have to write the structure of this molecule. So what he's telling, methane is the base, so CH4, but the hydrogens in the methane are substituted by different groups, that is phenyl dimethyl. Methane is CH4, so only one H will be retained because other three hydrogens are replaced by one phenyl and two dimethyl groups. So, and that CH it is lost because it is telling methane carbocation. Therefore, the structure is this. This is the methane carbon dimethyl phenyl carbocation. So it is one hydrogen short, that's why it has become carbocation. Now the question that he is asking is why the orthoproton absorbs at delta 8.8 ppm. So this is orthoproton, this is meta and this is para. He is asking this orthoproton is showing more de-shielding effect compared to paraproton which is appearing delta around 8.45. Now, when we look into the structure of the molecule, we can clearly see that there is a presence of carbocation. Carbocation will have less electron density around them. So, the presence of less electron density around the system will lead to de-shielding, and hence the orthoproton which is near to carbocation will have or will experience more de-shielding effect, and hence it is appearing more downfield when compared to paraproton. This paraproton which is far away from the carbocation will experience less de-shielding effect, rather it experiences shielding effect, and it is absorbing at 8.45, whereas orthoproton which is near to carbocation it will experience more de-shielding effect, resulting in the more chemical shift value, that is 8.80. So this is the probable answer for this kind of question. The second question is explain the NMR spectrum of ethyl 2,3-dibromo 3-para-tolulyl propionate. He's telling NMR spectrum, it can be either 1H NMR or C13 NMR. As far as today's module is concerned, we will stick to only 1H NMR. When such a problem is asked, he is not asked you to sketch the NMR spectrum, rather he has asked to explain the NMR spectrum of this molecule. Before you attempt this kind of problem, first you have to arrive at the structure of the compound. So here the base is toluene, that is toluene. Toluene is C6H5CH3, and to the para position you will have, because it is telling para toluene, to the para position you will have ethyl 2,3 dibromo. There should be a ethyl group, and to that ethyl group, to the each carbon of the ethyl group, there should be a dibromo, and followed by a propionate. Propionate is an ester with 3 carbon atoms. Therefore, the structure is this. This is the structure of ethyl 2,3 dibromo 3 para-toluene propionate. This is the molecular formula, and to that molecular formula, this is the structure that can be fit in. So this is the toluene group, C6H5CH3, but the para position is substituted, and hence at the para position we should go for this. So ethyl 2,3 dibromo, ethyl CH2CH3, but it is replaced or substituted by bromo. Here one bromo, here another bromo, followed by propionate. Propionate is CH3CH2COO. This is ethyl 2,3 dibromo para-toluene propionate. Now you have to explain the NMR spectrum. Whenever you are asked to explain the NMR spectrum of such compound, first you have to look into the multiplicity, and then you have to follow it by assigning the chemical shift values. Fine, let us start from this side. So this is methyl and this is methylene. So we have to apply N+1 rule here. CH3, it couples with this, it will have 2 protons in the neighbor, so it results in the formation of a triplet, and this couples with this and results in the formation of a quartet. Triplet and quartet is a characteristic feature of ethyl. Here we do not have any proton, but definitely there will be influence of this oxygen as well as this carbonyl. We will have both electronegative effect as well as anisotropic effect. Coming to this, here we have got H and here we have got H. So this couples with this and this couples with this. It results in the formation of 2 doublets. This will also give a doublet. This will also give a doublet. But we have to understand the fact that this proton will exhibit more value as well as this proton. This proton is attached or directly linked with bromo as well as carbonyl, whereas this proton is near this bromo, and also the effect of ring current from the benzene ring will also influence the chemical shift value. Coming to this benzene ring, this benzene ring is disubstituted, or we can say symmetrically disubstituted. That results in the formation of 2 kinds of aromatic protons. These 2 are HA and these 2 protons are HP. Obviously, HA will have more chemical shift value because of more electronegative bromine atom present near these hydrogens, and this is methyl, so this is electron releasing. That's why this HB will have lesser chemical shift value compared to HA. And now coming to the multiplicity of the aromatic ring, here the adjacent is H and this adjacent is H. There is only one H. It results in the formation of doublet. This also results in the formation of a doublet, whereas the CH3, it does not have any neighboring hydrogen. That's why it results in the formation of a singlet. We have finished the multiplicity. Now we have to assign the chemical shift value for each kind of proton. This is primary methyl, but this primary methyl, there will be an inductive effect of this oxygen, the electronegativity, and hence you have to write more than the regular primary methyl. So for regular primary methyl, we will write 1, whereas for this methyl, we have to write around 1.3. The value given here are approximate. You don't have to stick to the same values. You can slightly change. Change in the sense plus or minus 0.04. Up to that, it is acceptable. And this is oxygen and this is carbonyl. We know that oxygen results in electronegativity, carbonyl results in anisotropic effect. Hence, this methylene proton will definitely absorb more than 4. So we have written 4.31 here. And this is H. This H will have the influence of carbonyl and the bromo. So if the alkyl bromide is there, then it will come around 3.5, but there is carbonyl, that's why there will be more deshielding, resulting in delta around 4.8. Whereas for this proton, there is the influence of bromo as well as the ring current of the benzene ring. That's why among these two hydrogens which are near bromine or the ethyl of the compound, one proton will have lesser value, another proton will have more value because of bromine as well as the ring current of benzene. So this proton will have chemical shift value around 5.3. Coming to aromatic proton is always around 6.8 to 7.5, and as I said, this HA will have definitely more chemical shift value around 7.8 compared to HB, which will have chemical shift value around 7.1. The last is methyl. This methyl is directly attached to the aromatic system, so this is aromatic methyl. Definitely its value will be 2.35. In case if for the same question, if you are asked to sketch the NMR spectrum of this compound, we have to do the same thing, but there will be one more additional step. That additional step is sketching NMR. So what in that case, what you have to do, you have to plot the NMR spectrum starting from 0 up to the highest value here is 7. So you can go up to 8 and then mark 0 to 8 and then start writing the multiplicities and then assign chemical shift value for the particular proton present in this organic compound. The next compound is the next problem. An organic compound with molecular formula C5H8O2 gave the following signals in PMR spectrum at 100 MHz. What is the probable structure of the compound? For the first instance, when you look at the molecular formula, you can clearly rule out the fact that there is no aromatic system in the compound for sure. Because if there is an aromatic system, that is benzene ring, there should be minimum of 6 carbons. As we do not have C6 here, we have 6,5. We can clearly stick to the notion that this compound should be an aliphatic compound. So the PMR is run at 100 megahertz. It is immaterial for us now at this juncture. Now we will see the chemical shift value. Delta 1.33H triplet, delta 4.22H quartet. So presence of triplet and quartet, it indicates the presence of ethyl group, that is CH2, CH3, and they both will be neighbor to each other. And also we have to understand the fact that the usual ethyl will have around 1.2 or 1.3, but here the methylene of ethyl, it is more deshielded, maybe due to the presence of the oxygen. We have got 2 oxygen, we have to see what it is. The next value that they have given is 5.75, 6.10 and 6.40. So value between 5.5 to 7 or 6.5, it clearly indicates the presence of alkenic proton. Here there are 3 alkenic protons, one 5.75, second 6.10, third is 6.40. So we have given 1H, 1H and 1H. That means it should be definitely alkenic proton, and all are giving doublet of DD is doublet of doublet. So this is also doublet of doublet, this is doublet of doublet, and this is doublet of doublet. With this 5.75 and 6.40 having the coupling constant value 13 Hz, that means these 2 protons 5.75 and 6.74, they both are neighbor to each other, as well as the third alkenic proton, it is also showing doublet of doublet. That means among the 3 alkenes there is coupling between each kind of proton. So definitely we can say that it is an aliphatic compound having an ethyl group and 3 alkenic protons. When we substitute all this, so ethyl is CH2, CH3, C2, H5 is gone, C2, H5, 3 protons. So H5 plus 3 is H8. H8, all the protons are matched, and 2 alkenes means there should be minimum 2 carbon atoms. So here 2, here 2, 4. C4, H8 is already we have expected. The remaining is CO2. CO2 is definitely an ester, C double bond O. So when you arrive at the structure for this compound, this is the probable structure. Before this, you have to calculate the double bond equivalence. Because we know the molecular formula, we can easily calculate the double bond equivalent. The double bond equivalent for this compound comes out to be 2. That means there will be 2 unsaturations present in the compound. One unsaturation coming from the alkene, another unsaturation coming from the ester group, because CO2 is C double bond O. So one coming from alkene, another coming from carbonyl of ester. So we have got 2 unsaturations. Here you can clearly see that this is the ethyl group, one at delta 1.3, another at delta 4.2, and this is triplet and this is quartet. So here it is COO. Now we have to mainly concentrate on these 3 alkenes. Which alkene should have which chemical shift value? That is the question of the hour. Here all the 3 protons are chemically non-equivalent. That means to say that all the 3 protons are present in different chemical atmosphere. You can think that this HA, HB and HC, imagine these 3 are the protons, and all the 3 protons are attached to the alkenic system, and hence the value is falling between 5.5 to 6.5 or 5 to 6.5. Here now coming to this HA proton will either couple with this proton or it will couple with this proton. We can clearly see that this HB has got different background and this HA has got this HC. This is the neighbor, and hence this will couple with each other. HA and HC both will couple with each other. That means 5.75 and 6.4. 5.75 and 6.4. These two have got the same coupling constant value, meaning that these 2 protons are attached to the same carbon atom and they both are neighbor to each other. That's why we can say that HA and HC are coupling with each other. One is showing less chemical shift, whereas HC is showing more chemical shift. This HC is having more chemical shift value, maybe due to the presence of this ester. So in ester we have got oxygen electronegativity and carbonyl anisotropic effect. Whereas this HB, it is also doublet of doublet, because it is coupling with this, also it is coupling with this, resulting in the formation of doublet around 6.1. It is also showing somewhat higher value when compared to this HA, because this HB is coming into the cone of this carbonyl anisotropic effect. That means there will be definitely paramagnetic effect. Whereas this 5.75, because it is far away from this carbonyl as well as this oxygen, it will not be highly de-shielded. So this is the probable structure of the organic compound that fits to the molecular formula C5H8O2. Moving to the next problem. Give a structure or structures consistent with each of the following sets of NMR data. Under 4 we have got 2 problems. We will solve now 4A. Here the molecular formula of this compound is C9H10. C9H10, because there are more number of carbons and hydrogens. For the first look, you can think that there will be an aromatic system. That means there should be definitely a benzene ring. The proton NMR value that he has given is delta 2.04 2H quintet, delta 2.91 4H triplet, delta 7.17 4H singlet. For the first seeing, we can definitely assume that there should be a aromatic system that is also supported by the more number of carbons and hydrogens. 7.17 4H, it clearly indicates the presence of disubstituted benzene ring. And observe here one more thing, 7.17 is showing singlet. That means both the sides substitutions are same. We can say that symmetrically disubstituted benzene ring. Now the first thing that we have to do is to calculate double bond equivalent. To calculate the double bond equivalent, the formula that we use is CaHbNcOD, and Ra is relative abundance or double bond equivalent. You can calculate by using the formula A plus 1 plus C minus B by 2. So A here is 9 plus 1 minus 0 minus B is 10, that is hydrogen 10 by 2. So 10 minus 5 is 5. It indicates the presence of 5 unsaturation, including a benzene ring. So in benzene ring there will be 3 double bonds and 1 ring. 3 plus 1 is 4. Apart from that 4, there should be one more unsaturation. We will see what it is. Here PMR value, it is telling 2.4 quintet 2H. 2H indicates the presence of CH2, but it is showing quintet. That means there should be neighboring 2 CH2 groups. 2CH2. CH2 is 4. 4 plus 1 is 5. That means this proton at 2.4 should be attached to two more CH2s. Maybe it is within the ring because there should be one more unsaturation, and also you should see here that there is no oxygen. When there is no oxygen, the question of having carbonyl or hydroxyl or ester is completely ruled out. So definitely one more unsaturation should be coming from the ring. And another delta is at 2.97 triplet 2H, 4H. 4H triplet means there should be two CH2 groups, two methylene groups, and both the methylene groups are attached to a common CH2 group. And because it is showing quite de-shielded value of 2.91, I'm assuming that this CH2 may be within the ring. So this 2.4 and 2.91 together, they all will be a form. They all will be present in the ring. The last is delta 7.17 singlet 4H. It indicates the presence of symmetrically disubstituted benzene. Taking into consideration all this, the expected structure is this. So this is the benzene ring. Here there are 4 protons, so it should be a symmetrically disubstituted. Here there are 2 symmetrical, CH2, CH2 and CH2. So this is 7.17 singlet, and now we have to look into the quintet value. 2H is CH2, this is CH2. Quintet it is coming because there is one more CH2, there is one CH2 here. 2 CH2, 4 plus 1 is 5. That's why it is giving quintet, and this is giving triplet because this is common to this. It is these two carbons or these two protons having the same neighbor, common neighbor as CH2. That's why this couples with this. Here there are 2 protons. 2 plus 1 is 3. That's why it is triplet. Here also this is coupling with this. 2 plus 1 is triplet, and both are having value at 2.91. That is 2.91 triplet 4H. So this is the probable structure of this compound. Whenever there is a question like this in the examination, you should first calculate the double bond equivalent. Based on the double bond equivalent, you have to start assuming what are the different groups that could be present in the organic molecule. Coming to the second problem of the same type, C10H12. So there is no oxygen. Absence of oxygen indicates that there cannot be any hydroxyl or carbonyl or ester functional group. So 10 and 12 definitely indicates the presence of aromatic system. The NMR value given is 0.65, 2H multiplet, 0.81, 2H multiplet, 1.37, 3H singlet, 7.17, 5H singlet. So for the first C, we can definitely see that there is a presence of mono-substituted benzene ring. The remaining we will see later. First, we will calculate the double bond equivalent using the formula CaHbNCOD. Substitute this in A plus 1 plus C minus B by 2. 10 carbon plus 1 plus no nitrogen, 0 minus hydrogen is 12 minus 12 by 2. So 11 minus 6 is 5. So it indicates the presence of 5 unsaturation including a benzene ring. So benzene ring is there, benzene ring is there coming from the double bond equivalent. So benzene ring will have 3 double bonds, 3 and ring is 4. A ring is also considered as one unsaturation. So 4 unsaturation is satisfied. There should be one more unsaturation. To have one more unsaturation, we do not have any oxygen. So carbonyl or ester, everything is completely ruled out. Maybe I'm assuming that there could be one more ring in the molecule. We will see now. Coming to PMR values, 0.65 multiplet 2H. 2H indicates the presence of CH2 and he is giving multiplet. That means this proton should be attached to more than or more protons containing group. So it should be more than 3. If it is more than 3, then we generally call it as multiplet. Here also 0.81 multiplet 2H. 2H indicates the presence of CH2 and again this proton should be attached to more protons containing group. Another one is singlet 3H. It definitely indicates the presence of CH3. Usually for primary methyl it should be around 1. It is slightly more than 1. Then maybe I'm assuming that it is attached to a ring as we do not have any other unsaturation. The last is 7.17 singlet 5H. That means it is mono-substituted benzene ring. Therefore, the structure is this. This is mono-substituted benzene ring. Here we have got another ring that is cyclopropyl group to that extent that there is one more CH3. So this is CH2 and this is another CH2. This CH2 is more towards the ring effect of the benzene, ring current of the benzene. That's why it is having more chemical shift value compared to another CH2. This is near to electron releasing methyl. That's why it is showing less chemical shift value. And here definitely it is showing as multiplet because it is a small ring. We can not clearly identify whether it is a triplet or quartet. That's why they have given in general as multiplet. So this is one methyl group which is appearing around 1.37. I said earlier the primary methyl will be 1, but this is 1.37 because it is attached to the ring. So double bond equivalent is also satisfied in the sense that there are 3 double bonds plus 2 rings. 3 plus 2 is 5, so 5 is satisfied here. So this is how you will have to solve this kind of problem only when molecular formula and proton NMR values are given. The next problem is identifying the isomers based on 1H NMR values given. In that context, we will have this problem now. Identify the stereoisomeric 1,3-dibromo, 1,3-dimethyl cyclobutanes on the basis of their NMR spectra. We know that this cyclobutane having 1,3-dibromo and 1,3-dimethyl, it will exist in 2 forms, that is cis and trans. We have to identify which is which based on the NMR values they have given. First is isomer X, they have given delta 2.13, 6H singlet, 3.21, 4H singlet. So this gives a clue that there are only 2 types of protons. 6H singlet, that means there should be 2 CH3 groups. 4H singlet, there should be 2 CH2 groups. Now we have to write the structure of this compound. The base is cyclobutane, that is 4-membered ring with 1,3-dimethyl. Now we have to start numbering the cyclobutane as 1, 2, 3, 4. At first position you should have 1 bromo, and third position you have 1 bromo, and first position you have 1 methyl, and third position you have another methyl. It clearly seen here that both the types of protons are having same kind of chemical environment, and hence it results in the formation of singlet. That means there is no neighbor for these 2 types of protons. Based on this, we can arrive at the structure of the compound like this. So this is the cyclobutane. For that, this is the first position, this is the third position, or this is first or this is third. Because it is a symmetrical molecule, you can number it in any way. But first position you should have 1 methyl, 1 bromo, and in third position also you should have 1 methyl and 1 bromo. Because there are only 2 types of protons, we can clearly say that here it should be a cis isomer, because both the bromine one bromine and the another bromine are on the opposite side, and here 1 methyl and another methyl are on the opposite side. When such a case is written, you can have only 2 types of protons. One is methyl. This methyl is coming around 2.13 delta, and it is not having any neighbor, that's why it is singlet. And this delta will also have the same value as that of this proton, that is 2.13, whereas this CH2 will be inside the ring. That is the reason why it is showing somewhat higher value, that is 3.21, and it is also not having any neighboring proton. That's why it is appearing as a singlet. Whereas this isomer Y, it shows that there are 3 kinds of protons in this molecule. One is 1.88 6H singlet, that means there should be 2 CH3 and without any neighbor. 2.84 2H doublet, 3.54 2H doublet. So here these 2 CH2s, which is the part of cyclobutane ring, they should be present in different chemical atmosphere. So this is the structure of this compound. Here, this is the methyl group having 1.88 delta, and this is also another methyl group which is 1.88 delta. They both do not have any neighboring proton. That's why it results in the formation of a singlet. Whereas coming to the CH2, which is part of the cyclobutane ring, you will have two different atmospheres here. For this, you will be having more CH3 interaction and less Br interaction, because this Br is away from the plane of the ring. That means it is below the plane. That's why it is having less chemical shift value, 2.84, and it is giving a doublet because the interaction will be from this CH3 to CH2. That's why it is giving a doublet. Whereas this methylene group, which is near to bromo here, and that's why it is having 3.54, and this is also giving a doublet here. So this is the probable structure of the two isomers of 1,3-dibromo, 1,3-dimethyl cyclobutanes. The next problem, when methallyl chloride, the formula is given, methallyl, so allyl chloride is the base, to that is attached a methyl group, so it is CH2 double bond C. Here you should have one methyl because it is methallyl chloride. Allyl chloride is CH2 double bond CH, CH2, Cl, because it is given as methallyl, so one of the carbons is substituted with CH3. When methallyl chloride is treated with sodamide, sodamide is Na, NH2 in THF as solvent, a hydrocarbon with the molecular formula C4H6 was formed, and this hydrocarbon, that is the product, is obtained, which is having the NMR spectrum as given here. Delta 0.83, 2H doublet J is equal to 2 Hertz, 2.13, 3H doublet J is equal to 1 Hertz, 6.40, 1H multiplate. So the values of 1H NMR is given and is asking what is the structure of the hydrocarbon. So when such a question is asked based on the reaction as well as the spectroscopic data, you don't have to really worry about the writing the product in the first instance itself. Based on the chemical shift values or other spectroscopic values, you have to first identify the product and then you can write the product of the reaction. So C4H6, first calculate the double bond equivalent for this. When you calculate double bond equivalent for this, it comes to be 2. So how it can be 2, we will see now. When chemical shift values are observed carefully, you can see that 6.40 presence indicates the alkenic type group. There should be an alkene because the alkene value is generally 5.5 to 6.5 or 5 to 6.5. So it is falling within the alkenic range. So definitely there should be a alkene in this compound. Then where another unsaturation is coming from? Can it be carbonyl? No, definitely not. Can it be an ester? Definitely not, because oxygen is absent completely. So you can rule out the presence of carbonyl or ester in the compound. So it is completely a hydrocarbon. So you should have only carbon and hydrogen. Maybe I can expect that one more unsaturation is coming from the ring. When you take this methallyl chloride and treat it with sodamide, there will be a nucleophilic elimination reaction, because in the hydrocarbon there is no halogen Cl. So definitely Cl should be removed. When Cl is removed, there will be a formation of the ring, and that results in the formation of this product. So this product we can assign the values now. So 0.83 doublet, here there is one hydrogen. So 1 plus 1 is 2, that's why it is giving a doublet here. And 3H indicates the presence of CH3 because it is attached to an alkenic type, so it will be more deshielded. It is not ordinary primary alkyl, so it is more deshielded, hence the value is quite more, 2.13, and it is also doublet CH3 because CH3 is coupling with this H here. That's why 1 plus 1 is 2. That's why it is also giving a doublet. Whereas this is purely an alkenic proton having the value of 6.40, and it is coming as a multiplet here because there is CH2 here, there is H here. So 3 plus 1 is 4. Quartet instead of writing quartet, because it is a very small molecule, and also more than a small molecule, there is a small ring present here. That's why you cannot clearly identify the quartet. So instead of quartet, they have given us the multiplet. So this is the probable structure obtained when methallyl chloride is treated with sodamide in THF solution. So this is the obtained hydrocarbon. So here hydrocarbon, we have to match with the molecular formula C4H6, 1, 2, 3, 4. C4H6 is 3 plus 2, 5 plus 1, 6. So C4H6 is satisfied here, and also double bond equivalence is 2. One is coming from the ring, another one is coming from the alkenic double bond. Coming to the next problem. So this is definitely a composite problem, but given in another way. We will first look into the problem. A hydrocarbon containing 85.7% of carbon, 14.3% of hydrogen is transparent above 210 millimicrons in UV spectrum. In its IR, bands are formed at 3022, 1676 and 965 centimeter inverse. Two signals appear in its NMR spectrum. One is at delta 1.6 doublet, another one is at delta 5.55 quartet in the integral ratio as 3:1 respectively. Determine the structural formula of the compound. So this is a new kind of problem. Here they have given the percentage of carbon and hydrogen instead of giving the molecular formula. When such a case is given in the examination, you have to convert this percentage into number of hydrogens and number of carbons. Whenever there is percentage, you can clearly add these two percentages for 100, add up these two, this comes out to be 100. 85 plus 14 is 99, 0.7 plus 0.3 is 1, 99 plus 1 is 100, so it is 100%. Definitely it should be a hydrocarbon. There is no oxygen or there is no any other hetero element or any other halogen present in this compound. So UV is given, UV is telling that it is transparent about 210 millimicrons. That means presence of aromatic is completely ruled out. What about IR? IR it is showing 3022, definitely it is CH stretching frequency, but not definitely from the aromatic. 1676, I assume that there may be an alkenic type. Usually alkenes, it will come around 1500 to 1600, and this is 965. We will see what it is. Definitely it is from the fingerprint region. And coming to the 1H NMR value, there are only two kinds of protons. One is coming around delta 1.6 doublet. That means the neighbor should have only one hydrogen. And this is 5.55 quartet. This is definitely a CH having CH3 as the neighbor. So this is presence of doublet and quartet. It indicates the presence of CH and CH3, and it integral ratio as 3:1 respectively. CH, CH3, 1:3. So he is asking us to find out the structural formula of the compound. The first thing that we have to do in such a kind of problem is converting the percentage into number of carbons and hydrogens. So how can we do that? 85%, 85.7% of carbon, that is equivalent to 85.7 gram of carbon. So conversion of gram to the number, we have to do division using atomic weight of the particular element. So 85.7 divided by atomic mass of carbon is 12. 85.7 divided by 12, it gives to 7.1. And 14.3% of hydrogen, that means 14.3 gram of hydrogen. Atomic mass of hydrogen is 1, so 14.3 by 1 is 14.3. Now the carbon value is 7.1, hydrogen value is 14.3. We know that any organic compound cannot have carbon and hydrogen in the fraction, so you have to convert this into a whole number. Now start multiplying it by whole number, multiplying it by any integer to get the whole number. 7.1, start from 1, 2, 3, 4. We will see where we can end up. 7.1 into 1 is 7.1. Again, it is a fraction. 7.2 into 2 is 14.2. Again, a fraction. And 7.1 into 3, 7.1 into 4, it comes out to be 4. So 1 into 4, it gives 4 carbon, whereas this is 14.3 divided by 7.5. So instead of doing it by integer, you can also do it in this way. Divide it by the least number. Here the least number is 7.1, so 7.1 by 7.1 is 1. 14.3 divided by 7.1 is 2. There cannot be only one carbon and two hydrogens, so start multiplying it by integer. 1 into 2 or 1 into 3, 1 into 4. So it will be 4 carbon and 2 into 4 is 8 hydrogen. So there should be 4 carbon and 8 hydrogen present in the molecule. So IR 1676 centimeter inverse, it indicates the presence of alkene. As I said earlier, PMR 1.6 doublet and 5.55 quartet in the integral ratio of 3:1, definitely it indicates the presence of CH3 and CH, and also presence of 8H and 4C. It indicates that the molecule should be symmetric enough. So delta 5.55 indicates that it is an alkene. Therefore, the structure is this. It is a symmetrical molecule. It is butene, or we can say that it is 2-butene. CH3, CH double bond CH, single bond CH3. So this CH3 is coming around delta 1.6 doublet, because the neighbor is 1, 1 plus 1 is 2. This is alkenic proton having delta 5.55. It is coupling with CH3, 3 plus 1 is 4. That's why it is giving a quartet. So it is very, very simple. Whenever there is a percentage given, so percentage should be converted into number of carbons and hydrogen using this technique. So this percentage is implied to grams. That many grams divided by the atomic mass of the element, that will give a fraction. That fraction to divide it by the least number and multiply it by the integer to arrive at the number of carbons and hydrogens. Next problem. With the following details given below, arrive at the structure of the compound. Yes, given. This is also a composite problem. Molecular formula is C9H5NO4. So molecular formula, at the first seeing, it says that there could be a benzene ring because there are more number of carbons and hydrogens. IR 3000 to 2500, 2225, 1715, 1605, 1518 centimeter inverse. When you see the IR values, we can clearly come to a conclusion that presence of 2225 is the characteristic feature of an acetylenic type compound, either C triple bond C or nitrile C triple bond N. Definitely there will be a presence of triple bond in this compound. 1715, it is the characteristic stretching frequency of the carbonyl group. The rest we will see later. And PMR 11.1, singlet 5.3 squares. So 11.1, definitely it is above 11. It should be a carboxylic acid. 7.4 to 7.25, it indicates the presence of aromatic proton, but he has not given how many number of protons, rather he has given it in the squares. So you have to convert that squares into number of protons. And this aromatic protons, he is telling that it is present in the unsymmetrical pattern. That means it is not monosubstituted, it is not symmetrically disubstituted. Maybe it is disubstituted, but in the unsymmetrical pattern. Now first we will calculate the double bond equivalent using this formula. Substitute this in A plus 1 plus C minus B by 2, 10 plus 1 plus we have got nitrogen here, 1 minus 5 is hydrogen by 2. So 1 minus 5 is minus 4 by 2, 10 minus 4 by 2 is 2, 10 minus 2 is 2, that is 8. It indicates the presence of 8 unsaturations in the compound. Among 8 unsaturations, 4 will be for benzene, that is 3 double bond plus 1 ring. 4 is satisfied. We have to satisfy 4 more unsaturation. We will see how best we can do this. Coming to IR, 3000 to 2500 centimeter inverse indicates the presence of hydroxyl group. So because he has given it as broad, definitely there should be a OH group in the molecule. There are 4 O's here. There is 1 N here. 1 N, it can be either NH2 or NO2. We have to check what it is later. 2225, it is a characteristic feature of alkyne type. 1715 is the carbonyl. 1518, it indicates the presence of conjugated nitro group. So another functional group that we have identified is nitro group. Nitro group usually comes around 1500 to 1600. It will have 2 stretching frequencies, one for N double bond O, another for NO. So IR here in this problem plays a very, very significant role. One is telling the presence of hydroxyl, another is telling the presence of alkyne. This is about carbonyl and this is about nitro. Whereas coming to PMR, there are only two types of protons. One is 11.1. When you convert it into convert squares into proton, it comes out to be 1. How do you convert square? Divided by the least number, you will get some fraction multiplied by integer. You have to start from 1, 2, 3, 4 till you arrive at the number of protons given in the molecular formula. Singlet 1H indicates the presence of a carboxylic acid group. This OH of carboxylic acid group may be appearing here as 3000 to 2500 centimeter inverse as a broad. But if it is hydroxyl, it will be around 3300, and now we can clearly eliminate the chances that hydroxyl is not present. Rather, a carboxylic acid is present, and this OH is coming from the carboxylic acid but not from the hydroxyl, because the value is very deshielded. The most deshielded value in the proton NMR spectra is for the carboxylic acid. The next proton is about aromatic 7.4 to 7.5. He is telling there are only 3 protons. So in benzene, there should be 6 protons. Among 6, 3 are already substituted. The remaining 3 it will show in an unsymmetrical pattern. Based on this, we can arrive at the formula like this. So this is not 3. This is comes out to be 4. I'm sorry. This should be 4. This is 4 plus 1. 1, 2, 3, 4 plus 1 is 5 coming from the carboxylic acid. Definitely it is 5 protons coming here, and it is not 3. It is a mistake. I'm sorry. It should be 4H. So this indicates the presence of unsymmetrically substituted benzene ring. Now we will see this is carboxylic acid. Before that it is a benzene ring. We don't know how the substitution is, but there should be 1 alkyne group, 1 nitro group, 1 carboxylic acid group, right? So it should be definitely C triple bond C, COOH, and to that ortho position it is NO2. When such is the case, you won't see any symmetrical pattern. That's why he is telling that it has unsymmetrical pattern. With respect to the satisfaction of double bond equivalence, we will see what can be done. 4 is coming from the benzene ring. Remaining 4 we have to satisfy. Here we have got 2. 1 is coming from carbonyl 3. Another one is coming from nitro 4. 4 plus 4 is 8. So we have satisfied 8 unsaturation in the compound. And this proton is coming around 11.1 delta singlet NH 1H, because it is not having any other neighbor, so it comes out as a singlet. And this nitro does not have any hydrogen present in the molecule. That's why it is not showing. It is not shown in the 1H NMR spectrum. So this is how you have to solve when such a problem is given in the examination. Thank you very much.